Hello and welcome to another video. Today we're going to be working on word break. In this problem, you're given a string S and a dictionary of strings word dict, and you want to return true if S can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times. Okay, so for example, first we have LeetCode. So if we have LeetCode here, and our words are leet and code, we can see that we can obviously separate this, right? Because we can break it into two. So if we have we can separate it like this. So that part is pretty straightforward, and we can use the two words. Okay, our second word is apple, pen, apple. So apple, pen, apple. And the same thing, we can obviously, break that down. So if we have apple, pen, apple, we can break that into all the words we have. And then finally, for the last one, we have, so let's write that over here, cats and dog. And if we try to separate that, so we have cat and we have cats. Let's maybe try cat. So if we try separating with cat, then we do have, the only word we can use then is sand. And then we have this OG at the end that we can't do. So we have to go back. So maybe we could try cats. And now the only word we can use is and, but then we have this OG again. So no matter what, we have this issue that we can't get it to work, right? So this is going to be false. So you can kind of see from what I did there, essentially, so let's look at this cats and dog example one more time, right? So if we have cats and dog, essentially what we're doing, and we have the letters, or we have the words cats, dog, sand, and cat. This really helps us get a good intuition of what we're doing. Essentially, we're trying to break this word up any way we can and get a word that completes. So essentially, we're starting here. So let's make this bigger maybe, right? So let's take this cats and dog. Hopefully we can take it and make it bigger. We can do that, and let's bring it over here. There we go. Okay, so we're trying to start over here, and we're saying, okay, let's just go through this array and see how we can break this down. So we could use cats. Okay, if we break it down with cats, then we have this. Then we're over here at this index, and we can use the only word we can use here is and. Then if we break it down, we're here, and we can't do anything there, right? So if we have to recursively go back and say, okay, that didn't work. Let's try something else, right? Cats didn't work. Dog obviously isn't going to work because the word doesn't start with dog. Sand isn't going to work. And isn't going to work, so we have to use cat. So we break it with cat. Then we check over here. What's the only word that works here? It's sand. And then we have this OG again, which is a problem. So that's our algorithm. Kind of just, let's just write that down. So start at an index. Loop through the available words and keep trying to cut with that word. And then if we can, recurse. If not, go to next word. And our goal is to go through the whole string, right? So our goal is to end up at the very end of the string, and it all needs to be cut up into pieces. That's our goal. So if we just do that without anything, how long would that take? So actually, you could pretty much do this, and if you actually do that, right, that would actually work, except you need one more step, which is you need memoization. So you could literally just start here, and you could say okay, let's just go through all these words, wherever index we're at, and let's try every single one, and if we ever get here, then we say, all right, we did it, good job. And so that's actually what we're going to be doing, but we're going to add a caching, and that's actually pretty much the algorithm. That's literally all it's going to be. So we're going to have a recursive algorithm. Now let's just write the state, right? So we're going to have a DP algorithm. Let's write the states. So let's write the state. So we're going to have a DP, and let's write, our variables in our state and things like that. So parameters, all we really need is just the index we're at, right? Pretty straightforward. Okay, what's our base case? Our base case is the index is length of s, that means we're done, so we can return true. Now we also have a visited, and in this case we actually only need a visited set, because if you think about it, if you ever get a true, if you ever get a true, that means you were able to parse the whole word, and we don't need some optimal parsing. We're not asked like parse this in as little words as possible or as many words or whatever. So if we ever actually get a true, then we'll be done. So we only need a visited set, meaning like if this index is in the set, that means we tried from there and we failed. So it's going to be a visited set instead of a visited hash map as normally. Now what's a recursive case? Try every word in the words array to see if it fits. And then if it does, let's recurse and update index. And that's pretty much it. So we're just going to do that. We're going to have a visited set. And if we ever get a success, if we ever hit the base case, then we're done, because we're not asked to split this up in some optimal way. We're just asked to split it up, and if it's possible or not. And that's actually going to be pretty much it. So now we have enough to start coding now that we know kind of what we're doing. We're essentially doing like a brute force with memoization, and that's pretty much, I think, as good as you can do for this problem. You might be able to do something like a try, but this works too. So, and this is DP, and I think DP is better than a try. I think try is one of those like, if nothing else works, then use a try. Everyone tries to avoid the try. Okay, so let's do that. So we're going to have a visited set, and then we're going to have a DP function. We're going to have an index, just call that I, and we're going to say if, and I actually want to initialize this because I'm going to use this, so let's just say length or something equals length s minus 1, because we do need to actually check where the last variable is, and I'll show you why that is in a second. So if I equals length s, that means we're done. That means we've hit success. So we can just return true here. Okay, now what are our other cases? So if I in visited, we can return false, because everything in visited is false. Because if we ever hit a true, we're not going to store it in the visited. We're just going to return all the way out. So we're going to return false there. Now we need the recursive case. So the way we are going to do this is we're going to go through every single word in the word dict. So we can say for word in word dict, right? And then we're going to need to match the letters. So essentially we're going to need to match the letters in the word dict to all the letters in the word. But also let's think about this case. Let's say this word leet is actually like leet and then 1,000 more characters, and we're at this character. So we don't want to be comparing here and then just be out of bounds. That wouldn't be good, right? So we're actually going to check, is our string even long enough to hold this word? And if it's not, then we're just not even going to bother checking. So that's what we're going to do here. So we're going to say if I plus then length of the word, so that's going to be word minus 1. And the reason it's minus 1, if you think about it, so let's say we're at index 0 and the word is 2 characters long. What's the last character of the word? Well, the word is going to fill up index 0 and index 1. So the last character is actually going to be at index 1. So that's why it's length of the word minus 1. This should be minus 1. So if I plus the length of the word minus 1 is greater than length, this length variable here, that means we're out of bounds for the string. So we don't need to check this word. So we can just say continue here. Otherwise, let's go through the word. So we can say for j in range length of the word. Now we can compare character by character. So if, what are we at? We're at si plus j, right? So let's say we start at index 0, and this word is like 5 characters long. That means the first character will be at index 0, then the second character will be at 0 plus 1, 0 plus 2, 0 plus 3, and you get the point. So that's why you have this I plus j, because you're essentially, that's where you need to be looking. Okay, so for I, if you could also, I think there is literally a method to check, like if there is a word, like if you give it a starting index and you give it a word, it will actually check for you, like, is that a match? But I'm just doing this way because you might not be allowed to use something like that. You know, you want to be able to come up with it yourself. So essentially, if si plus j does not equal word j, that means there is no match. So we can just break here and then move on to the next word, right? We don't need to keep checking the rest of this. We're done. Now we finally need one more check, and that's if the last character is, so if j I guess this would be if j equals length word minus 1, that means we've actually checked every single character in the word and every single character in the string, and they are true. So if they are true, now we need to do our recursion, right? Like let's say we did this leet, so we compared leet to this, it's all good. Now we need to call dp with the next index. So we're going to do that. So we can actually have another if statement. We can say if dp of, and then this is going to be I, this is going to be I plus j plus 1, right? This is the current index we're at. We need to go to the next one. So if dp I plus j plus 1, I believe, let's just double check. So let's say the word is 2 characters long. So we would be at character 1 for the next one. And then this would be, yeah, I think that's right. This would be I plus 1, and then this would be plus 2. So I think that's correct. Okay. So now, if this is true, that means we've successfully made a break, so we can just return true here. We don't need to like save anything. That's why I said we don't need to have a hash map here. Okay, and if it's not, then we're just done with that loop, or done with that iteration of the loop. Now finally, when we went through every single word, if we didn't find anything, now we just simply say visited.add this index, meaning if you ever get to this index again, this is like a no-go, this fails. Then we can return false here. Because you can get to the same index multiple times, because let's say we have like LeetCode, but then you have like Apple or something, LeetCode, right, where you have these leet and code words. But then your other words, you can get here multiple ways. So let's say you also have like app and LE, but then you also have A and then PPLE, right? So you can get there 2 ways. You can go Apple or you can go Apple this way. And so you're going to get to this same part multiple times, so it doesn't really matter how you got here. All it matters is you did. Okay, so now we need to do return false here, and now we just need to call. So we need to call dp at index 0 and return that. So we're going to return here, and hopefully that's all correct. Okay, looks good so far. Okay, so you can see it's quite efficient, and yeah. And so let's think about the time and space complexity here. And we're going to think of the time and space complexity in terms of probably characters is a good way to do it, right? Like imagine, there's some number of characters. What are we actually doing? Because, yeah, that's probably the best way to do it for strings. So let's think about that. So time, what are we actually doing? Well, let's think about it. So first of all, how many states do we have? So we have length s states. So that's just going to be like, let's just call that n, right? Like this can be anything in s. Okay, now every single time we are looping through every single word in word dict. And so let's just say that's like times the number of words, right? And also we are comparing every single letter in every single word to the string. So worst case scenario, we have to check the entire thing. So let's just say, this would be like worst case, like max of words or something. Like max, this would be like the max length of a word, something like that, right? That would be the time. Essentially, you're saying like, okay, we have to go through the string, we have to go through all of the words. So like this is word dict, and then also we have to compare character by character. So we actually have to go through every single character in every single word, whatever that is, right? So let's say every single word has 5 characters and there's 20 words, whatever, like 100. So technically we could write it as well like this. So we could write it like n times number of characters total in word dict. That would also be fine. It would actually be like more, yeah, no, actually that would be correct. Something like that. Worst case scenario. You'd have to check every single character in the word dict every single time for every single state. So it's something along those lines. And if we actually look at like how long that would be, so this would be like, so words length is like 1,000, and then everything has 20 characters, so let's just say that's 20. And then s length is like 300, something along those, right? So how many zeros is that? 3, 6 zeros. So it'd be like 6 times 10 to the 6 or something roughly would be worst case for these constraints. Something along those lines. Okay. And so let's go through the space. So the space is a lot less because we only have a set and it's just going to have booleans, right? So this set only has booleans. We're not storing any anything else. We're just storing booleans. So this is actually O of n, because you can only have n states. That's like O of like 300 or so in this case. not that bad. But yeah, so it's important to recognize you need a set instead of a hash map just to save some space, and because you can recognize that like one successful state means you're done, and that's going to happen with a lot of problems. Like one success means you're done, then you can use a set instead of a hash map because you're basically saying, okay, well we don't need to see the value at all of these; they're all just going to be false because if we ever hit a success, then we're done. But yeah, that's going to be it for this problem. Hopefully you enjoyed it, and if you did, please like the video and subscribe to the channel. It really helps grow it. And I will see you in the next one. Thanks for watching.